you know. All right, I'm gonna get ready to send this thing. All right, I'm going to send over the slides. I left a lot in just because a lot of the stuff is pretty technical, and you guys should, if you're doing the iPad thing, take notes over it. It's good. Let's see, people are here. Just wait one more minute. Okay, let me know if you guys get that. Perfect. Okay, let's get going. Okay, today we're talking about enzyme catalysis and glycolysis, enzyme kinetics, metabolic components. It's mainly section 7 of the Biochem 2 book. If we have time, we're going to try to get into glycolysis, which is in section 8, the metabolism part of the Biochem books. So obviously it's a lot to do, but ideally you've maybe flipped through that chapter, and we'll start covering that stuff and doing practice questions. Okay, and so the first thing we'll do, free energy and equilibrium. And so today, talking about enzymes, these are the the 3 bullet pointed, very general, energetic principles of enzymes, right? Like the Newton laws of enzyme kinetics, right? And someone asked, if we don't finish glycolysis, yeah, we're 100% going to cover glycolysis. I mean, ideally today, if not when we start talking about metabolism officially, right? And so just to go through these, right? Enzymes are catalysts. They do not alter the equilibrium of a reaction. Okay, enzymes can accelerate the forward and reverse reaction by the same amount. Okay, and so what enzymes actually do is they accelerate reactions by stabilizing the transition state. Okay, right? And this can be symbolized as delta G activation energy, right? Or delta G, you might see it as a delta G double dagger, right? Okay, so enzymes accelerate reactions by decreasing this activation energy right here, as you can see in this. Okay, and so but for any of this, these reaction coordinate diagrams. For any of this really to make any sense, what we really need to do first and foremost is to have a better understanding of delta G, right? What the heck is delta G, right? It's free energy, but what is that? Okay, and so we're going to come back to all this enzyme talk, but first we got to talk about where does delta G come from? All right, and it comes from the Gibbs equation. Okay, I know you guys have seen this before, right? This is delta G, the change in free energy, right, is equal to the change in enthalpy, which is heat released or absorbed during the reaction, which by itself does not predict if the reaction is favorable, right? You need that in combination with temperature times the change in entropy, S, right, which is the measure of randomness. And again, delta S does not predict whether a reaction is favorable or not. What does is the combination of them, right, which gives you this delta G, the change in free energy, right? And what this is just the energy available to do work, okay? And as delta G approaches zero, right, it's approaching equilibrium, okay? And so delta G is used to predict whether a reaction is favorable or not. All right. And, we cannot measure, free energy. We cannot measure just G by itself. So we have to measure the change in free energy, delta G. Okay. And so, depending on, the different contexts you're talking about delta G in, there's different ways of writing it and slightly different meanings. And so we're going to, try to define what each one of those is. Okay. So you need to know that G, gives free energy. You need to know that delta G is the change in free energy. And then we get to something called delta G naught. And this is delta G under standard conditions. Okay, what are standard conditions? That's when the products, right? The reactants in the products are going to be in equal concentrations of, 1 mole per liter at, STP, okay? Which is pH of 0, 25 degrees Celsius, and an atmospheric pressure of 1. Now, I don't know about you, but we're biochemists right now, and we're never, ever going to run into a situation where we're going to have a pH of 0, a temperature of 25 C, and a pressure of 1. It's just not going to happen, okay? So when we're talking about delta G in a biochemistry context, right, you're going to see delta G written as delta G naught prime, okay? And so that's just, delta G under standard biological conditions. All right. And so that's going to be where your pH is physiological, right? You're going to be at body temperature, and you're going to be, still at an atmospheric pressure of 1. Okay. So for biochemistry, delta G naught prime, indicated by that little prime marker there. Okay. So let's take a look at this here. This is a triangle, and I'm not sure if you guys have seen this before ever, but it's pretty cool. This is a triangle relating how, free energy is related to, the standard cell potential, E cell, right? And how it's also related to equilibrium, the equilibrium constant expressed as K. Okay. And so, you can connect these three values, expressions, whatever you want to call them, with, various different formulas, right? And so, over here, do you guys know what this is? Okay, cool. You guys haven't talked about this yet, right? This is the Nernst equation, right? And it's going to come, yes, exactly, in your electrochemistry class. Nernst equation. Okay, so we don't have to worry about that, but when you're in your general chemistry, you guys are going to be talking about this. Okay. For what we care about when we're talking about biochemistry, when we're talking about enzymes, enzyme equilibriums, enzyme kinetics, is we care about how free energy is related to equilibrium, right? So we actually use this equation here. And so this is what we're going to be talking about today. Okay. And R, you guys have seen R before. This is that, the constant, right? It equals 8.314, joules per mole, or oops, joules, oops, per K minus 1. Okay. You guys have probably seen this before. That's just that constant number, okay? All right. Does anybody have any questions about this? So again, we're going to be focusing on how delta G relates to equilibrium, right? And equilibrium can be represented by products over reactants, okay, as you see here. Okay, so from the Gibbs equation, right, just like I was saying, we get this equation, which we're going to call the free energy and equilibrium equation, okay? Delta G equals delta G naught prime under standard biological conditions plus RT, log of the KEQ, the equilibrium constant, okay? And, for reference, right, usually the KEQ in your body for most reactions is going to lay somewhere between 10 to the -2 to 10 to the -8 molar, right? And you're going to get these standard free energies of around -3 to a -12 kilocal per mole. All right. Okay. And so if we wanted to kind of draw this out to better understand it, and we wanted to solve for either K or for delta G, right, we take our reaction and we can plug them back into this free energy and equilibrium equation, and you can get this delta G equals delta G naught prime, right, plus RT ln of your KEQ. Okay. And so when we're solving for delta G, we could further rearrange this, and then again we can further rearrange it. And here you see that we're just switching ln out for log base E, okay? And so delta G equals delta G naught prime plus RT log E of KEQ. And so here, this is important. Remember that in a biological system, we're always in equilibrium, right? So I'm going to even write that down, right? In a biological system, we are always in equilibrium. Okay, so what does that mean? That means that we can just take our delta G and we can eliminate it. And so if we're further solving for our delta G naught prime, you can just rearrange the equation one more time, move everything over on the other side of the equal sign, and you get delta G naught prime equals -2.303 RT log 10 of KEQ. Okay, and that's how we get this equation here. Okay, which is what we care about in our biological system. Okay. When someone says, why are we always in equilibrium? So your body is always in equilibrium, right? Anything that happens to your body immediately does reactions to get it back to equilibrium. Okay. And where did the -2.3 come from? Okay, that's a very good question. The -2.3 comes from, it's just rearranging. You see how this is log E to RT log base 10, right? If you remember your moving around logs and natural logs, right? ln of x is equal log x divided by log of 2.7, whatever E is, right? And it actually gives you this number here. Does that make sense? Yeah, and at equilibrium, our delta G is 0, but not our delta G naught prime, because that's under standard conditions of 1 mole product, 1 mole reactant. Okay. And so, again, for the MCAT, you're not going to have to rearrange these equations. Okay, so don't be freaking out about that. What we're trying to do is go through a step-by-step manner to how we're arriving at certain equations, just so you can have a better understanding of what they are. Okay. And so if we wanted to keep going, and then instead of solving for delta G naught prime, we wanted to solve for KEQ, you can just further rearrange it down, and you get this right here, which is KEQ equals 10 to the, delta G naught prime divided by, 1.36. All right. Okay. And I think one of the, someone says equilibrium instead of homeostasis. What do you mean by instead of homeostasis? Right. All reactions in the world are moving towards equilibrium, right? So anytime you make a change, it's going to adjust to shift it back into equilibrium. Does that make sense? So if you, eat extra sugar or something, you're going to, break that down into equilibrium. Homeostasis is just the processes for your body to stay alive, to be in, constant, whatever it is, pH constant, whatever your sugar levels are, constant temperature, blah, blah, blah. Does that make sense? I got one yes and a not really. I think this is one of those things that's going to just become, you're going to understand this more as we keep going, right? When we're looking at delta G, not prime, right? We're using this number to predict which way a reaction is going to go under standard conditions, okay? All right. So let's just keep going here, and I think it'll work itself out. So, to better understand one of these equations, right, it's good to just plug in a bunch of numbers. Okay, so let's plug in a bunch of values for KEQ, right, and see what that means in terms of delta G naught prime. Okay, so if we start here with the percent B, right, here's your products, and here's your reactants A, right? Then you're going to have 0.99 over 99. So you're going to have a really small KEQ, okay? And then that's going to correspond to a large positive delta G naught prime, okay? And as the KEQ increases, right, you're going to notice that the delta G naught prime gets smaller and smaller and smaller until you have here a very large negative delta G, okay? So what this means is the bigger the KEQ, right, the bigger the negative delta G naught prime, okay? Which means that the reaction is more favorable. Okay. Does everyone follow that? So as our KEQ gets bigger, right, you're going to get a bigger negative delta G naught prime. So the reaction is going to be more favorable. Okay. So now let's apply this, i.e. smaller. Yes, i.e. smaller, exactly. Thank you for pointing that out, right? A bigger negative, right, aka a smaller delta G. If you read like a, like a textbook or something, usually like the paper or something will say a bigger negative delta G, to kind of emphasize that it's going to become more favorable, right? But yes, i.e. smaller. Okay. So let's now look at a reaction coordinate. Okay. And remember that, the spontaneity for a reaction is based on delta G and not delta G naught prime, okay? Delta G naught prime is just under your standard biological conditions of 1 mole product, 1 mole reactant, you know, at physiological pH, temperature, whatever, okay? And so here, right, this corresponds to a negative delta G, right? Which means that there is a net loss of energy and the reaction will go spontaneously, right? It's said to be exergonic. Okay. And so I think we should maybe, you know, kind of reel it back here, and hopefully this will clarify what you guys are talking about. And looking at, you know, the hypothetical examples, right, under different conditions. Okay. Oh, sorry. Someone wants to go back. Okay. So this is a negative delta G in red, which is a net loss of energy, which is exergonic. Cool. All right. So let's look here, like at a hypothetical example, right, illustrating different conditions. Okay. And, you know, today we're going to be talking about glycolysis. So let's use an example. Oh, someone says, can you explain exergonic versus exothermic? I can do it quickly, and we're going to explain it more later, right? Exergonic is a loss of energy, right? We're losing free energy. So it's exergonic, all right? And endergonic is a gain of energy, right? So exergonic versus exothermic would be like similar, right? Exothermic, you release heat, right? Exergonic, you release energy, right? Exothermic means heat, right? So it's like the same thing, but instead of free energy, we're talking about heat, okay? And is exothermic spontaneous? Yes, but not, yeah. You would be going back to this, right? So it could be spontaneous if everything else aligns, AKA your entropy. And that's, you know, we're not going to go into that, okay? Well, let's look at these examples here, right? Where we have an example of, you know, glucose 6-phosphate going to fructose 6-phosphate. And it's given that we have a delta G naught of +4 kilocalories per mole. Okay. And so if we look at a non-equilibrium situation, the standard situation, and an equilibrium situation, right? Can we predict which way each reaction is going to go? Okay, cool. Yeah. Thank you, guys. Okay. So my question is, if delta G naught is positive, you know, can the reaction favor the products? Okay, so here's a situation where the delta G naught is positive, right? Can the reaction favor the products? Okay, and the answer is yes, right? Absolutely, as long as the K value is small enough to have a negative delta G, okay? So let's look here in the non-equilibrium reaction, right? You have a very small K value, right? 0.09 over 0.9, right? And so your K value is small enough that if you plug it back into here, right? And you plug your delta G naught into here, you're actually going to get an overall negative delta G, okay? Which is illustrated here. So which way does the reaction go? The reaction is going to go like this. Okay. So now let's look at it under standard conditions, right? So standard conditions, again, 1 mole, 1 mole, right? In standard conditions, delta G is just equal to delta G naught, right? What's ln of 1? right, of 1 over 1, this is just equal to 0. So delta G is equal to delta G naught. Do you guys see that? Okay. And so under standard conditions, it's delta G naught that's going to be able to predict which way the reaction goes. And in this case, oh, sorry, and I messed this one up, flipped it. Right? Delta G naught is positive, right? So it's actually going to favor this direction. Do you guys see that? If delta G naught is positive, it's going to favor the reverse direction. So it's going to favor the substrate. It's going to favor A. Okay. So here, if it's positive, it's going to favor A. We'll make these arrows a little bit more clear. Right? This has got a negative total delta G, so it's this way. Okay, what about at equilibrium? Okay. At equilibrium, delta G is equal to 0. So no direction. All right. I think I wrote all this out here. Yep, exactly. Does anybody have any questions on this? Does this clear up, you guys' questions before? Someone says, why is standard delta G not 1 if 1 over 1 equals 1? Because 1 over 1 does equal 1, but natural log of 1 over 1 is equal to 0. Okay, so if you take this, right, plug it into here, this whole thing goes to 0. So delta G is equal to delta G naught prime. Okay. Cool. Nice. Okay, let's go over the non-equilibrium one more time. Okay. So it's given that delta G naught is positive, but we're in non-equilibrium, and you'll notice here that the KEQ is very small, right? You have products 0.09 over the reactants 0.9. So you're going to get a very small number, and it's going to be small enough, right, that your overall delta G, this species, is actually going to be negative. So you're going to get this going into the forward direction. Does that make sense? Got it, right? So because your KEQ is small, right? AKA you have, right? Someone just asked me a question, I don't quite understand. Yeah, it'll be in the forward direction, right? Because the delta G overall is negative. Okay. Does anybody have any more questions on this? Yes, yes, exactly. So if you go back over to here, right? Cool. Okay, great. So right, to summarize, if delta G naught is equal to 0, right, and KQ is equal to 1, A and B favor neither direction, right? Or if delta G naught is less than 0 and KEQ is greater than 1, products are favored. and if delta G naught is greater than 0 and KEQ is less than 1, reactants are favored. Okay. So I thought bigger KEQs meant more negative delta G, right? Yep. So plug it into this reaction here, and you'll get these values. Okay. All right. So let's talk about, oh, hold on one second, something. Sorry, hold on one sec, guys. Cool. Sweet. Cool. All right. Sorry about that. Something just came up. All right. So let's talk about coupling reactions. Okay. So the delta G naught of two reactions are additive in any sequence of two or more reactions. Okay. And that's the same with delta G. Okay. So you'll notice here, right, that glucose plus ATP to glucose 6-phosphate and ADP has a very large negative delta G naught prime.
Hey Josh, sorry to interrupt. There's like a thread going on in the chat. Would you be able to kind of clear that up a bit?
Okay, yeah, let's see. Which, can someone just unmic and ask the question?
Yeah, I think it's just clarifying again, so someone's saying like a small KQ equals a negative delta G or vice versa.
Okay.
So yeah, someone's just saying, can you clear up the delta G thing?
Gotcha. So here's delta G naught prime, right? Just start, the best way to understand these kind of equations is to just start plugging in the numbers, okay? What happens when you take a KQ of 0.01 and plug it into the equation, right? You're gonna get a positive delta G naught prime. And as this number gets smaller, as the KEQ gets bigger, right, you're gonna have a bigger negative delta G naught prime.
Got it, because it's like a positive by multiplied by negative.
Yeah, exactly.
Okay, cool.
You see that?
Hi, sorry, can you hear me?
Yeah.
So, I think we all understand this. So the bigger the KQ, the more negative the delta G. But then when you went into the following example, when we were on the non-equilibrium one, you were saying because it's a small KQ, it's a negative delta G, which just contradicted the info you gave us on the previous slide. So now I'm confused.
Because look at this. Right? We're talking about delta G and delta G naught prime. Okay. So let's just plug everything right back into it again. Right? You have 0.09 over 0.9, right? Into your ln of KQ times RT plus the delta G, which is positive 0.04. Okay. And then you're going to actually get a slightly negative delta G, in this case, just barely. All right. Yes, thank you, Sophie. Nice. Haha. Cool. So the big thing you guys need to know, the number one takeaway thing, right, is that the delta G naught prime, right? Delta G naught prime is going to predict which way a reaction goes. Okay. So if the delta G naught prime is negative, it's going to predict if the reaction is going to go forward. If the delta G naught prime is positive, it's going to predict that the reaction is going to favor the substrates. And yeah, thank you, Sophie, for translating that. Awesome. Does anybody have any more questions? Right? Because this is important. Cool. Okay, so coupling reactions. Let's move down to here, back to coupling reactions, right? So you can imagine like a biological pathway. You're going to have some reactions that are favored and some reactions that are unfavored, right? So how does anything get done? And that's because you can couple multiple reactions in a row, 2 or more reactions, and you can just take the sum of those delta G's, right? And as long as the sum of those delta G's are negative, the set of reactions, right, the pathway can proceed forward, right? So here's a good example, again, from glycolysis, where you have a negative, right, which is very favored, and then you have something that's not favored, right? And so for the only way to go from glucose 6-phosphate to fructose 6-phosphate is having it coupled with another reaction. In this case, glucose plus ATP goes to glucose 6-phosphate plus ADP. Okay. And I think this is a really great way to visualize delta G, right? So you can imagine a negative delta G is a loss of energy, right? You're losing energy. But if you couple this big loss of energy with a different reaction, right, you can actually, store some of that energy up, right? So you can imagine this orange corresponds to this, and this big negative corresponds to this, right? So you can recapture some of that lost energy in this big negative delta G, right? And store it back up in this positive delta G. All right. However, okay, we're talking about whether a reaction is spontaneous or not, right? But what we haven't talked is about the actual rate of reactions, okay? The actual rate of a reaction depends by lowering the activation energy by enzymes that catalyze the reaction, which is now what we're going to get into. Okay. But first, let's do a quick practice question. We'll do 4 minutes and then start guessing your answers. And then we'll talk about it. Should we take another minute? Maybe 30 seconds. Let's speed this up. Okay. We've got one for B. Anybody else have any guesses? Got a bunch for B. Cool. Okay. We got one for D, and we got one for question 2D. Okay. So this may be not a fair question because we haven't talked about glycolysis yet. Okay. But the answer to 1 is actually A. Right. Now, if you're familiar with glycolysis, right, the reason you can get to this answer super quickly if you knew was because this step in glycolysis actually produces an ATP. Okay. So of course, this is going to have a bigger negative delta G than all these ones that burn an ATP, right, for it to work. Does that make sense? Okay. Right. And so like if you read the question, right, which of the following reactions releases the most energy under standard biological conditions, right? This is just, in other words, what reaction has the largest negative delta G? And so you would use information in the passage. And if I were to use any information in the passage, I would use this right here. These bonds are high energy because of the associated electronegative charges exerting a repelling force between phosphate groups. So let's make this a bit more of a fair question for you guys. And let's get rid of this as an answer choice. Okay, this is going to be really good. And you guys should know this for your MCAT. Now what's the answer?